All right, scholars, so we're going to go ahead and get this titration lab underway. So I've kind of already set some things up here, so let me tell you what I've done. So this is my burette, and if you remember from class, in the burette we're always going to want to place the titrant. And today we're doing a strong acid, strong base titration. So right now, in my burette, I have placed some sodium hydroxide, which will serve as my strong base. And then here in my Erlenmeyer flask, I've placed the analyte, which is my strong acid. A few quick notes about the burette. You may be able to see that the volume readings here are upside down. They're backwards. Remember, the burette is a helpful piece of glassware for noting changes in volume and not total volume. And so basically the burette is going to help me keep track of how much sodium hydroxide, how much strong base titrant I have added to my analyte. And that's really the only data that we're going to need to collect for this lab. I suppose the purposes of this lab are to just walk you through the steps of titration, and kind of show you that it is a valid method of chemical analysis. I know that the concentration of sodium hydroxide that I have in here is 0.1 molar, and I know that the concentration of hydrochloric acid, strong acid I have in this Erlenmeyer flask, is also 0.1 molar. I have 70.02, you can see it right behind me, 70.02 milliliters of hydrochloric acid in here. And so, because this is a strong acid, a strong base, and they're the same concentration, 0.1, 0.1, if I have 70.02 milliliters of my strong acid in here, I should also expect that I'm going to need 70.02 milliliters of the strong base to reach the equivalence point. So, you may be wondering what this is. This is a pH meter. And this is basically a handy little electronic device that is going to help me measure the pH level in this solution. So what we can do is generate a nice lovely titration curve like you see on the top up there. That is my strong acid, strong base titration curve. But I would also like to give you a visual of the equivalence point. And so, to my analyte here, I've added a few drops, just a couple drops of this. This is phenolphthalein. This is an indicator, and it's a really good indicator to use for strong acid, strong base titrations. It has a very wide range of pH where it will change color, and basically it changes color whenever there is excess hydroxide ions. So, think about what I'm doing. I'm going to be slowly adding hydroxide ions to my acid, to my HCl. They're going to perfectly neutralize until I add my hydroxide in excess. The moment that I add one drop of sodium hydroxide in excess, this thing should change color. It should turn magenta. I want just a faint magenta color, and that should be the equivalence point, because then I know that I've added equal amounts of HCl and NaOH titrant from my burette. Make sense? So hopefully we see that happening around 70 milliliters of my NaOH being added. And as I said, we'll be able to keep track of the pH as well. A quick note about the burette. You can see that the burette is quite, well, first of all, it's broken down here at the bottom, but you can just pretend that it's not. The burette is quite narrow, and so it's really sensitive to any error. I don't know what was in this burette beforehand, so I needed to clean it out pretty well, so I rinsed some water through it. And now think about this. If I rinse water through this, and then I immediately pour in my sodium hydroxide titrant, do you think I'm going to get good results? No, if I just pour some water in this and let the water run through, there's going to be a little bit of water clinging to the sides of the glass burette. And when I add my sodium hydroxide, it's going to dilute my sodium hydroxide a little bit. And so it's going to take more of the diluted sodium hydroxide to have the same effect, more sodium hydroxide to reach the equivalence point, And if I didn't know what the concentration of this was, I could get a skewed value, a value that's skewed too high, because my sodium hydroxide in reality was too dilute because there were a few water droplets in there. So whenever you're preparing a burette for titration, you always need to rinse it and wash it twice. Once with water, and then you actually need to rinse it and wash it through with the titrant that you're using. So I actually rinsed it through with my sodium hydroxide. Another reason why you want to do that is so that you can fill it with your titrant all the way down here to the bottom of this nozzle. Because as soon as I turn this knob, the valve will open, my sodium hydroxide will start flowing. I'm going to be able to track those volume changes as it goes down. And so I need my sodium hydroxide to already be occupying all of the burette, all the way down here to the bottom of the spout as well. So you'll see that I have this over a waste beaker so that I can just allow the sodium hydroxide to flow through, fill all the way up to the end of the spout before I actually start my titration, right? So let's begin the titration. Okay, so you can see now that I've placed my earthenware flask, which has my acid analyte, hydrochloric acid, underneath my burette. I'm basically going to start dispensing. Now, before I do need to get that very careful reading of the initial volume of sodium hydroxide in there. Remember, I'm trying to figure out how much sodium hydroxide, what volume I had to add to reach the equivalence point. So I need basically two pieces of data. How much volume did I have before, and how much volume did I have at the end? And I subtract those, and that's going to be the total volume of sodium hydroxide that I added. So, very carefully, we need to interpret what each of the little tiny lines represents, and they represent a change of 0.2 milliliters. So right now it looks to me like this is, looks like my meniscus is right at about 11.2. If that's kind of tricky for you to see on the camera, don't worry about it. But every little line is 0.2. Every larger line is a change of 1 milliliter. So how many sig figs can I get with this measurement device? It's capable of reading, the lines represent 0.2 milliliters. So I believe that I get one extra decimal place, right? So I can get out to the hundredth of a milliliter. So remember that sig figs are based on measurement, based on what kind of glassware you're using. This can get me out to 2 decimal places. Okay, so you can see that I've written that my initial volume is 11.20 milliliters, and let's start dispensing our base. Now, what's kind of difficult for you guys to see on camera, but what I can see quite clearly here is that whenever I dispense base initially, I see momentarily some very faint pink. Let's see if I can get you guys in on that action. Right when I dispense the base, I see just for a moment some light pink. That's because, again, the phenolphthalein will change from clear to magenta in the presence of excess hydroxide. So I have to stir it around to get the hydroxide to react with the H plus ions from my strong acid so that it will react away. And I'm looking for just the faintest pink color. I'm getting close to 70, so we said it could be about 78 or so. So I need to titrate it until I get the faintest pink color that just remains. And it is getting more and more difficult for that pink color to fade away. So I need to add it very carefully, drop by drop now. I think you can see that the pink color is indeed remaining. Oh, we're so close, my friends. Let's see. Not yet. I truly do, once I reach this point, just want to add that base drop by drop, because I do not want to go past the equivalence point. Ooh, it's such a faint pink. I can't tell. Wish you guys were here to help me. Nope, that is still clear. Alright, so let's add, oh boy, we're almost there. Just a drop more. And that is it, my friends. I think I accidentally added 2 drops. But you can see the difference that, that occurs right when you add a drop or 2 drops. When you're near that equivalence point, the whole thing becomes very, very sensitive. Just a drop excess hydroxide in your phenolphthalein will change color, and that's it. That's the equivalence point. So now I need to get this final volume and get a reading for that. So let's see what the final volume of NaOH was that we added. Of course, we're just going to subtract these numbers. So the volume of titrant of base that we ended up adding was 73.10 milliliters. So what can we conclude from this? What kind of calculation can we do? Well, pretend that we didn't know what the concentration of that acid was. We can use this to discover what it must be. Remember, this indicator has shown me when the equivalence point occurred. And we know that the equivalence point means when your titrant and your analyte are present in stoichiometrically equivalent amounts, so they completely consume each other, completely react away. So if this is how much titrant it took, if this is the volume of titrant it took to get me there, then I can do some calculations to figure out the concentration, how many moles per liter of acid of my analyte there must have been. Okay, so here you can see the table ladder that I've set up. This is the volume of sodium hydroxide, titrant that we had to use to reach the equivalence point. I know its concentration is 0.1 moles per 1 liter. I know that sodium hydroxide and my hydrochloric acid will react together in a 1-to-1 ratio. Maybe you could write out that chemical equation if you so desired. And then I know that I had 70.02 milliliters of acid originally in that flask. So that's the volume of acid. This will get me moles of acid divided by volume of acid will get me the concentration of acid. Now, I told you originally that the concentration of acid I was using was 0.1. I was using 0.1 sodium hydroxide and 0.1 molar acid. However, one of those things is not the case. If that was exactly true, if I did have exactly 0.10 molar sodium hydroxide and 0.10 molar HCl, then it should have taken the same volume of the base to neutralize away the acid. So someone is lying to us, or there's been some error that has occurred. Maybe whenever I rinsed this with water, maybe there was some water left, and maybe my sodium hydroxide was actually in reality a little tiny bit diluted, which would mean that we would need more of it, 73 milliliters instead of 70 milliliters. Or what's possible is that my stock solution of acid is a little bit old, and maybe some of the water evaporated away. So if some water evaporated away from this, then that tells us that in reality it is more concentrated than 0.1, which means it would take more base to neutralize it away. So those are probably two pretty good theories. Either my base was too dilute, or my acid was more concentrated than I originally thought. So if this is truly not a 0.10 molar acid solution, based on our data, what is the concentration? Well, perform that calculation and you'll see.